Hi everyone, there's a team 1125 and I'm Wenhao Huang. My other two teammates are Yuxuan Wang and Weijia. All of us come from New York University. And today we are trying to solve the problem C, people rule everything. Here's the content we will introduce in this video. So first, let me introduce some background information. As we know, the presence of people will affect how animals behave. In other words, it will affect the population of animals, including herbivores, carnivores, and omnivores. Prey animals become less varied and become less likely to engage in behaviors that reduce the risk of predation after repeated exposure to human activities. And nowadays, there is an existing model to illustrate the relationship between predator and prey. And for this problem, we are trying to figure out how some other human factors will contribute to this relationship. So we want to create a mathematical model of a system of animals that interact with each other and are exposed to human activity and explore the long-term implications of what happens when prey animals have some of their anti-predator responses muted. Our model will be divided into three parts. The first part is to illustrate the interaction between three kinds of animals before humans move into the system. And the second part is to find out the interaction between them after humans move into the system. And finally, the most important part is to figure out the interaction between three kinds of animals after humans move out of the system. So before we construct this model, we made some assumption. And we used the population as the parameter to describe the relationship between different animals. And we want to construct a plot between the population and the time. And we assume that only three types or groups of animals exist in this ecosystem, and the intelligence of an animal affects the lifespan of the animal. And there will be unlimited food supply for herbivores. And the logic to solve this problem is to try to find the factors that affect the population of animals that can be quantitatively expressed. So the first model, we construct three expressions to express the rate of increase in animal population. The X will represent the number of carnivores, and the Y represents the number of omnivores, and the Z represents the number of herbivores. And the expression of the rate of increase is shown on the slide. And also we construct a loss of constant for this problem. So we find a solution for equilibrium point for these three equations, and the value of them are shown on the slide. After that, we use the computer to make a simulation and construct a plot between the population and the time. So the first plot is when t equals to 16, and the blue line is the herbivore, the red line is the carnivore, and the green line is the number of the omnivores. The second plot is when t equals to 100. And based on these two plots, we can see that the population of all of these three animals is like oscillation.
Our model 2 represents when humans move into the system after animals have been living in the system for a while. So we define the equation representing the wary degree of an animal, Wt, and with greater value of Wt means the animal is more wary, which means they will have more anti-predator responses. And A determines the lower bound of the graph. The range of W should be 1 minus 1 over A and 1. And in the equation, B represents a parameter that's proportional to 1 over L, with L being longevity of the animal. And we assume that animals who have longer lives are more intelligent, so that they will respond quicker to the human influence. And C represents the population number of an animal group, and D represents the living area of the animal group, which are all like relevant to the speed of how animals corresponds to the human influence. And the constant C is set to equal to 1, so that the value of W is positive between 0 and 1. And we use the values for WT such that the range of WT is between 1.5, and we use NumPy to simulate the human influence in the system by substituting the W parameter to the predator-prey equation from the previous model. And from the simulation, it's easy to see that when humans enter at t equals 20, the animal like population, especially for the herbivore, drops significantly, which makes sense as like their anti-predator response is shut off, and they are more easily killed by the predators. And our model 3 represents the interaction between the 3 species of animal after humans move out of the system. And VT here is representing the way humans, like after humans left the system, how animals vary degree change and recover to their previous levels. And VT is really similar to WT, except it's like reverse, with 2 minus t being its variable. And we substituted V into the denominators for the P1, P2, P3, and C1, C2, C3 coefficients. And from the simulation, when human enter at t equals 20 and left at t equals 60, the populations of the 3 species didn't return to normal levels. And we also simulated more rounds, and it's interesting to see how, like, when t is 22 and when human left at t equals 28, at time t equals 28, the system actually survived longer, and there's more oscillations, which probably means the ecosystem is more stable than the ecosystem as when human left only 2 time units after they came to the system. And this shows that the factors that influence the stability of the system is not necessarily the amount of time that humans have stayed. Instead, it's the point of time when human left, because at t equals 28, the values of the populations are closer to the initial values, which would generate a pattern of oscillations that's more similar to the oscillations from Model 1. And our model tells us that before human move into the system, the population of 3 species oscillates when their initial population are in the equilibrium state, and after humans move into a system that was in equilibrium state, the populations of herbivores will decrease significantly because the predator response is shut off, and the stability of the ecosystem is destroyed. And after human abandon the area, the model has shown that the stability cannot be restored. So our model concludes that is that the overall impact in a system in which human quickly abandon the area. The result shown in this model means that generally human moving out of the system can now restore ecosystem and has caused damage. If human move out of the ecosystem at a point such that the population of the three species are equal to the initial values, and when their wear degree returns to normal, the human influence on the ecosystem would be minimal. And our model could be improved because the equilibrium found for the first model without human influence was not perfect. Because we can see the amplitude of the oscillation was still increasing gradually, so the oscillation will stop after a long time as the amplitude hits the x-axis, and the ecosystem is just not stable anymore. And what caused it is because we didn't use decimal numbers to represent the initial condition of the population, because that wouldn't make sense. But if we could come up with parameters that such that the population such that the solution for the equilibrium state had whole numbers of population, the model would possibly act more stable. And we also could have modeled the competition of resources between herbivores, so they cannot just grow exponentially, and if there's like no predators around them. And we also could have built on this basis and add more species to the system, so that the model is more representing the reality. And this is the end of the slide. Thank you.